video off, and please make sure that your audio is down or is off as well, so that we're not getting feedback and we get a clean recording. All right. So again, what we're going to be talking about today are the non-renewable resources that we use, and again, that we've become dependent upon for the last 100 years, give or take, and understanding why we use those resources. And the answer to that question deals with two factors, and those two factors are net energy and subsidies. And so let's walk through what that means. So let's start with net energy. I want you to think about net energy the way that you would think about, I want you to think about net energy the way you would think about kind of like, net income, right? So net income is how much money you have left over from your paycheck after you've spent money for the week. And you can either be, in the positive, you can be in the negative, or you can be even. Those are the three options in terms of net income. And with net energy, it's the same thing. It's how much energy do you have left after you've used energy to extract a resource from the ground. And so when we're talking about net energy, I want you to recognize that, even within some of these different resources, you can have different amounts of net energy based on how difficult or easy a resource is to extract. So the official definition of net energy is the total amount of useful energy available from a resource minus the energy that's needed to make the energy available to consumers. And we're going to go through and talk about coal, oil, natural gas, and uranium today, and understanding what the net energy is for each of those. And you can also think, again, when we're talking about a return on investment, we can think about an energy return on investment. And it's the energy obtained per unit of energy used in order to obtain it. And so a lot of times we'll talk about that as the energy content. We'll talk about that as, BTUs per ton, for example. BTU is British thermal unit. You could do joules, right? But BTU is the most common one when we're talking about fossil fuels like coal. And it's a unit of energy that we're thinking about, and how much energy is available in a resource, and then deduct how much is necessary to make that resource available for us. And the reason that this is true, and let me back up a second. It's not so, like, if we extract a hunk of coal out of the ground, it's not that we're actually taking energy out of that hunk of coal. That's not what I mean. It's when we're balancing our energy budget, right? When you're thinking about how much energy we have available, if we're using a bunch of energy to pull one resource out of the ground, and that resource doesn't provide us with more energy than what it took to get out, then it doesn't really make sense. But believe it or not, we actually do that in a couple of instances. So when we talk about net energy, I want you to recognize that when we're extracting oil, or we're taking coal, or we're fracking to get natural gas, it requires energy in order to make that resource available for us. And it's a decision that we make, right? We're making a conscious decision to use this energy for the purpose of extracting a resource, so that we can then use that resource to turn it into some other kind of energy. And so what that means is that we're going to have to spend some of our energy budget in order to get these resources out of the ground and available to us. And as we've talked about before, the second law of thermodynamics tells us that we can never get close to 100% in terms of our energy transfers. So even in this extraction game that we're talking about now, there's all kinds of waste heat that's generated through these processes, and you're going to lose energy. You're going to be transferring energy into forms that are not as useful to us at every step of that transfer. All right. So why are we talking about net energy? Well, the reason is because that certain resources, and natural gas from fracking is one of them, cannot compete in a true open market because of their net energy. And so what I mean by that is when we frack to get oil or natural gas out of the ground, that is a non-traditional form of energy, okay? A non-traditional form of oil or a non-traditional form of natural gas. And so what that, sorry, what that means is that if you take an oil field in Saudi Arabia, for example, that oil is close to the surface and it's very easy to extract. It's in a liquid form. It comes out of the ground with very little effort, right? So that means that if you take 2 barrels of oil, one from Saudi Arabia and one from Colorado, where we're extracting oil with fracking, the oil in Saudi Arabia, even though chemically it's identical, the oil in Saudi Arabia has a higher net energy because it requires less energy to extract than the oil that we're pumping out of the ground in Colorado using fracking. Fracking is much more energy intensive. And so even though those 2 barrels of oil with the same chemical bonds, with the same potential chemical energy, when we think about it as an energy budget, the Saudi Arabian oil is going to have greater net energy than the oil from Colorado. But we want to, in the United States, we want to support our oil and natural gas industry, and we have for over 100 years. And so the way that we do that is we subsidize it. So we make a fuel that that should not be on the market based on what the market will bear. We make that fuel available because we subsidize those industries so that they can compete against less expensive forms of energy. So what are we talking about here? Like, actual dollars, almost $5 billion a year that we use to subsidize those 4 industries: nuclear, which is primarily uranium extraction, and then nuclear power plants. Nuclear power is one of the most expensive forms of energy there is. But again, because we subsidize it, it makes it affordable. Coal, oil, and natural gas. So almost 5 billion. And if you, for whatever reason, are struggling to sleep at night, this document right here, and this is where a lot of the material comes from that we're going to talk about today in terms of subsidies. It's incredibly boring, but really pretty important in terms of understanding how we subsidize these industries. So again, if you can't sleep, that'll put you to sleep pretty quick. All right, so let's talk about oil. And again, we're talking about conventional versus unconventional. The OPEC member nations, right? And OPEC is the organization of petroleum exporting countries. And a lot of times people think OPEC is strictly a Middle East entity, but there are countries in South and Central America that are part of OPEC. Nigeria is part of OPEC. So it's not just countries in the Middle East, but it is primarily countries in the Middle East. And most of the oil that is under the OPEC umbrella is conventional crude. And what we mean by conventional crude is in its natural state under the ground, it's a liquid. It is relatively easy to extract. And as a result of that, it has a medium net energy because it doesn't require a ton of energy to get out of the ground. Now, we need to remember that using oil the way that we have causes all kinds of air pollution. And again, primarily we're talking about carbon dioxide, but there's other issues. And we've looked at what happens when we burn gasoline in our tanks, and we've talked about catalytic converters and nitrogen oxides and ozone that form as a result. Anyway, it also causes water pollution. Now, one of the things here that I want to make sure that you write down is that those things, the air and the water pollution, those are called externalities, right? External, and that's an econ term, but externalities deal with issues that result from using a product that you're not paying for when you purchase it. And so one of the things that we want to do is we want to talk about what the true price of a resource should be. And so not only are we subsidizing this resource to make it less expensive to use, at the same time, we are not paying the full price associated with its use, right? So we're not paying for the climate change that happens as a result of driving cars that run on gasoline. And so one of the things that people often talk about doing in order to correct the issue of climate change and make us burn less fossil fuel, they call it capturing externalities. And so capturing externalities means that you're paying for climate change every time you buy a tank full of gasoline, for example. And so make sure you recognize that idea of externalities and how we can capture externalities. The most common way to capture externalities from gasoline would be a carbon tax, which we've talked about. All right, so that's conventional oil. Unconventional oil has all of the same negative effects associated with use and then some. It is harder to extract. There's oil shale and tar sands. The Canada in Alberta, and Alberta is a province directly north of us. And in Alberta, there are massive deposits of this tar sand. But instead of the oil being in a liquid state the way it is in conventional crude, oil that's trapped in shale or in tar sand is not a liquid, it's a solid. And so it takes an incredible amount of energy to extract the oil from that sand or rock. And as a result of that huge energy input required, even though the oil is identical, right? It's identical oil in terms of the chemical bonds. It has a lower net energy because of the amount of energy required to extract. And honestly, in addition, the negative effects of using oil from shale or sand are even worse. Incredibly water dependent, incredibly energy dependent, much more pollution results from it. But as we deplete the conventional oil resources, we're largely left with these unconventional sources of oil. And if we insist on burning oil, this is what we're going to be burning, right? We're going to run out of the conventional stuff. That's the easiest to get out of the ground. It's the cheapest. And without subsidies, oil from shale or sand would still be in the ground. And so the US government and the Canadian government subsidize the extraction of oil from those two kind of varieties. And we put it on the world market because the government supports the companies and gets the cost back down. Just as a frame of reference, oil coming out of unconventional sources, in order to break even, they need to have oil on the world market be priced at around $70 a barrel. And oil hasn't been at $70 a barrel in well over a year. I think the last time I looked, it was trading at about $33 or $34 a barrel. And so that means that every barrel of oil that we produce in the United States from shale and every barrel they produce in Canada from the tar sands, they're losing money, probably $30 or $40 per barrel on that extraction technique. And obviously they're making up for it with that subsidy from the federal government. So why is it that we're doing this, right? I mean, it doesn't make sense to use resources that we have to extract resources that wind up having a lower net energy. And the reason we're doing it is because we have reached a point where there is more unconventional oil left in the world than there is conventional. And so a lot of times we talk about this as peak energy or peak oil. And so peak oil can be described as like the moment, right? Peak oil is the moment that our production or extraction of oil has decreased, right? So it's turned the corner and it's starting to go back down. And so we've been able to put off peak oil because we've started extracting this oil from other places. Now, one of the other reasons that oil has a lower net energy, so either a medium or a low, depending on conventional or unconventional, is because the crude oil that comes out of the ground is not useful to us at all. It has to be refined. And refining it again, requires a bunch of energy. And normally we would spend a couple days talking about oil refining. But we're too pressed for time, and we're gonna move through it. But just understand that when we talk about refining oil, we're talking about separating the oil into those hydrocarbon chains that we've discussed. And so the longer the hydrocarbon chain, so for example, asphalt comes out of a barrel of oil. So asphalt, what we use to pave our roads, comes from oil. The shortest of the hydrocarbon chains, the really short ones that come out of petroleum products, we use to make things like makeup, right? So they're really short hydrocarbon chains. All kinds of plastic comes from those shorter hydrocarbon chains. So there's much more in a barrel of oil than gasoline. And so I just want you to think about that as we go forward. And so this is just a really good graphic, I think. When you put crude oil into a refinery and you heat it up a little bit, it'll start evaporating at different boiling points. And so the shortest boiling points, or the shortest hydrocarbon chains, have the lowest boiling points. And then the longest hydrocarbon chains have the highest. And again, this is just a partial list of all of the different products that we get from oil. So just bear in mind that. All right. So we've been talking about the royal the global community has been talking about are we running out of oil or not? And when I sat in my first environmental science class 30 odd years ago, I was told we only had 30 some years left of oil. And I'm going to sit here and tell you we have about 30 years left of oil. And the reason that my teacher those many years ago was not wrong is because we have found new ways to extract oil that we knew was in the ground. So 30 years ago, we didn't know how to do fracking. We didn't know how to extract oil from tar sands or from shale. And so we've developed new technologies to access that stuff. Now, somebody has often said, or normally I'll get a question that says, when are we going to use the last drop of oil? And the reality is we're never going to use the last drop of oil. What will happen is that as we continue to run out of the conventional oil, the extraction for the unconventional sources will become so expensive, it'll be cost prohibitive. I'd like to think that the environmental damage associated we'll start to recognize that, and we'll start to capture some of those externalities, and we will, we'll turn off the pump, right? We'll stop using that stuff. So the answer is yes, we're running out of conventional oil, and we know that because it's a finite resource. Now, what is going to be interesting is the rate at which we continue to use it. A report has just been released by the UN, the Intergovernment Panel on Climate Change, the IPCC, and they've said that CO2 levels during the pandemic, people thought at one point that CO2 levels were going to decrease this year, and they haven't. We're still increasing the amount of CO2 because even though we're not driving, we're certainly burning a ton of coal and natural gas to make electricity. And because we're staying home, we're using even more electricity. So I'd like to think that at some point those environmental costs, the externalities, will be captured, and we'll stop burning oil. But who's to say when that's going to happen? So are we running out of conventional oil? Yes, it's a finite product, and it's going to become more expensive as we have to shift to the unconventional sources. Now, this is heartbreaking. This is ANWR. This is the Arctic National Wildlife Refuge. You guys know how much I love my acronyms. So ANWR, it's pronounced ANWR. This is in Alaska. This is the breeding ground for the largest caribou herd in North America. And it has been protected for, forever, right? I mean, since the U.S. Acquired Alaska in I think it was the 20s, Stewart's Folly, if you're a history person. ANWR is an important ecological preserve. It is also, it has a deposit of oil present. The current president of the United States has opened up this pristine wilderness that's never been touched, right? No human habitation. It's one of the most pristine Arctic ecosystems there is, and he's opening it up for oil exploration. Now, it's hard to say whether or not that is going to be codified into law or if it's something that can be reversed under the next administration. But this is something that's been fought over for a really long time. And to put it in perspective, if you know, and the oil companies have said, based on the size of the deposit, it'll take us somewhere around 50 years to build the infrastructure to access the oil that's in Anwar. And so that dip you see down here at the bottom, this is how much oil we would get from Anwar. And then this line right here is the projected consumption of oil in the United States. It really doesn't do anything for us. You know, it's something that a few oil company executives have wanted, but the reality is it's such a harsh environment. The extraction would undoubtedly be marred by oil spills, and you would destroy a pristine ecosystem. And why now we're I'm baffled, and I'm almost speechless, but you guys know me well enough to know that I'm not really speechless. I'm incredibly irritated that he wants to go in and pull oil out of here. It makes no sense financially. Like never mind ecologically. Think about the triple bottom line. We can't pull oil out of Anwar at a reasonable price and even hope to put it on the market unless there are massive subsidies. And that's unfortunately what the president is suggesting. So remember Anwar, that's definitely something that's going to come up on the test. And it's something that I mean, just look at that picture. It's absolutely gorgeous. And it would be an absolute shame to have oil spilled in that entire river system. And it fronts up on the Arctic Ocean. So it would be a spill into the ocean as well. All right. So we talk about externalities. What are the environmental costs associated with this? Obviously, we're going to disrupt ecosystems. We're going to increase our greenhouse gas emissions. And on top of the greenhouse gas emissions, we have other forms of air pollution that we've talked about. The nitrogen oxides, the particulate matter that comes from burning fossil fuels. In addition, there's water pollution, and then there's loss of biodiversity. You know, that the example of Anwar is part of the reason it's so troubling is, you know, this herd of caribou, it's their breeding ground. And if you damage that ecosystem and they no longer have a clean ecosystem in which to breed, then that herd is going to go extinct. And we are in the midst of a mass extinction event, which we'll talk about next semester. But guys, you know, we're losing species on this planet faster than we can count them. And so losing biodiversity is incredibly important. In terms of accounting for our CO2 emissions, this is 2019's number, or I'm sorry, this is 2018's number. I haven't found the number for 2019 yet, but just under half of all CO2 comes from oil. We talked when we did the energy mix in Colorado that the biggest energy user in Colorado is the transportation sector. And so when you look at the United States, when you look at you know, a few other nations, the transportation sector is the one that consumes the most energy. And so that's certainly the case here. 43% of global CO2 emissions come from burning oil. And you know, when we think about sustainability and we think about self-reliance, I think it's important to note that we produce 9% of the world's oil. We consume about 25% of it. We have just under 2% of the world's proven oil reserve, and we import 52% of the oil that comes from that. You know, this is a losing game. You know, this is something that cannot be sustained. It's not going to. It's not going to last. You know, this is a finite resource, and we're using it up like it's infinite. And I just think these numbers point that out pretty well. So when we talk now about heavy oil or unconventional oil, 72% of it is in the Western United States, and then in Canada as well. And it's shale or it's a tar sand, and it is, instead of being a liquid, it is a solid. It is incredibly water and energy intensive to get it out of the ground. And as a result of that, the net energy for this unconventional oil is incredibly low. There are places where the net energy is actually negative, meaning it takes more energy to get the oil out of the ground than the oil would give us. But the reason that we do that, which is, you know, which it's illogical in so many ways, but the reason that we do it is because we use oil so much for so many things, where we have an abundance of coal. And if we can use the energy in the coal to extract the energy in this shale and get the oil out, we think that that is a logical decision to make, because the oil is useful to us in transportation, where the coal is not useful to us in transportation. If we transition to an electric vehicle fleet so that everybody drove electric cars, then we could use the coal to drive the cars and we wouldn't need this oil. And so our net energy would be better than its current situation as a result of that. And again, it's not to say that, and this is an important thing that you guys keep in mind, you know, not everybody who drives a Tesla is driving a clean car. If you're charging your car off of the electric grid in West Virginia, for example, then you're running your car on coal and it's incredibly dirty. And there's an activity that I hope we're going to be able to get to next week, where we actually will quantify emissions coming from hybrids versus electric versus traditional vehicles, and we'll look at what the energy mix has to be in order for an electric vehicle to make any sense. So just remember that most of the oil that we're producing in the United States carries with it an extra burden of environmental and economic costs. And I know it's hard for you to visualize what oil shale looks like. And that's a rock, that's shale. Shale is a sedimentary rock. And so the microscopic organisms were laid down between layers of clay, which is what makes shale. And that oil can be extracted from that rock using high pressure steam. So you've got to heat up the water to the point that it's beyond boiling. You need to have that water in a compressed form so that it stays as a steam, and then you inject it into rock, and you're essentially melting the rock in order to extract the oil. So incredibly energy intensive. But again, this is what we're down to, is we're extracting oil from a rock that looks like that. So we talked about, excuse me, we talked about tar sands up in Canada, and the deposits between Canada and Venezuela are larger than all of the oil in Saudi Arabia. And again, it's tempting. And I asked this question when we were looking at the Gapminder activity, and I asked you whether or not a country would be inclined to think about one part of the triple bottom line differently if they had an abundance of oil. And I can tell you that that's the case in Canada. In Canada, they recognize that they have greater oil deposits than all of Saudi Arabia, and if they extract them, they can be, you know, largely independent from any other foreign government in terms of meeting their needs. And so that idea, that goal of being energy independent, at least in this one sector, has led them to make these really irrational financial and energy net energy decisions that normally you wouldn't make. And OPEC does some really fancy footwork in terms of, you know, they drop the price, and if they keep the price of oil low enough, then they know that these governments, the U.S., Canada, Venezuela, these governments have to subsidize the oil industry in order for these deposits to be accessed. And obviously, Saudi Arabia and OPEC, They don't want us extracting oil from these reserves because it starts cutting into the monopoly that they have. And so we make these really irrational decisions based um, on on flawed logic in a lot of ways. So just remember that there's incredible environmental impact associated with it. The harder it is to get out of the ground, the lower the net energy is. And the harder it is to get out of the ground, the higher the cost associated. But we do it anyway because we see this resource and we think it'll make everything better if only we could get it out of the ground. All right. This is a visual of kind of what we were discussing before with the oil shale. They inject steam in to the ground. So you see the water being heated on the surface. And again, it can be heated with oil, it can be heated with coal, it can be heated with whatever resource you may have access to. And so you inject that steam under high pressure and high temperature into the ground. The rock begins to break apart, and then they extract or pump the oil back out of the ground. And so that is how they do it when it is on site. In situ means on site. And then the other way that they can do it is they can dig down and access the shale in what they call a pit mine, and they pull the shale out of the mine, and then they transport it to a facility. And at the facility, they will do the same thing. They'll heat that rock up with high pressure steam and extract the oil. Most of the world's reserves are in locations or at depths that you are not able to use a traditional open pit mine to extract it from. And you have to do the in situ extraction technique that you see on the right. The in situ leads to all kinds of subsidence of the Earth's surface. So you get things like sinkholes, you get earthquakes. There's an increase of earthquakes as a result of this activity taking place. And we're causing those earthquakes to happen. All right. So let's transition to natural gas, keeping in mind that that oil is the most finite of these three fossil fuels. Natural gas is next in line, and there's much more natural gas than there is oil. Again, in Colorado and in the Western United States, we have natural gas that is trapped in these layers of rock in this shale. And in order to get the natural gas out, we need to break it apart. So conventional natural gas is similar to conventional oil. It is easy to extract. It has a medium net energy, a low production cost financially, and it's cleaner burning than oil. And remember, cleaner does not mean clean. When you burn natural gas, you're most likely only to get carbon dioxide and water vapor coming off of it, probably a little bit of nitrogen oxides, as we've talked about before. Getting it out of the ground in a conventional way is not that damaging because in its natural state in the ground, it's a gas. And so you typically don't get a natural gas spill like you would an oil spill in water. The natural gas would evaporate at lower temperatures, and it doesn't create as many environmental problems in terms of extraction. Most natural gas, somewhere between greater than 50%, depends on the deposit, is methane. And a lot of places, methane is flared. And what I mean by that is the methane is such a small hydrocarbon chain, it's difficult for it to be captured on site. And so they'll burn it on site. So it'll look like a giant Bunsen burner out in the middle of a field, and they're flaring the methane off, and then they're capturing the longer hydrocarbon chains. And then when they are transporting it, they transport it either as LPG or LNG. And you can think about propane, for example. The reason that propane, when you grab a propane tank and you kind of you swing it around and you can feel a liquid moving around, it's a liquid because it's under pressure, and then when you release the pressure, it comes out as a gas. And so when we think about conventional natural gas forms, LPG or LNG are the ways that they extract it, they transport it in that method, and then typically we burn it in one of those two methods. All right, so where do we get our oil? We get the majority of our oil out of shale, and again, shale extraction happens as a result of fracking. And fracking is incredibly energy intensive. It's incredibly water intensive. Guys, this is one of those mysteries that, you know, every company, every oil and gas company has their own proprietary fracking fluid. And so what I mean by that is they have ingredients that they're mixing in water and injecting in the ground, and they claim that it's proprietary, which means that it's like a secret that lets them do business the way that they do business. And as a result of the proprietary nature of that formula, the EPA is not regulating this because the EPA doesn't know what's in those fracking fluids. And so we're injecting these fluids into the ground in places on the East Coast where we have very shallow aquifers, and where those aquifers are used for drinking water, the aquifers are contaminated with these fluids. And if you go to YouTube, and maybe I'll throw a video up for you, it's frightening. There's people in Pennsylvania who can actually light their water on fire. So they turn the faucet on, and there is so much natural gas blended into the water coming out of their well that they can use one of those long grill lighters and light their drinking water on fire. And it's not made up. This is not fake news. This is the actual real news. And so fracking is dangerous for a ton of reasons. In the Western United States, our aquifers are incredibly deep, and the natural gas deposits are above them. And so typically we get less contamination of our aquifers. And in Colorado, we don't use our aquifers for drinking water. We're dependent upon surface water for that, which is mostly snowmelt. But in other parts of the world, we have contaminated drinking water from fracking fluids. And so this is kind of a step-by-step approach to how fracking works. It's very similar to what I showed you with the extraction of oil from tar sands and from shale. But in this instance, what they're doing is they're pumping water into a shale formation, and inside the water is, again, all kinds of proprietary chemicals. But there's always something like there's sand, right? And they push sand into the water because when they push this water into the ground under high pressure, it causes fissures to appear. It causes the rock to break apart. And then if you release the pressure, the rock would just go back together. So you inject sand into the well at the same time, and the sand particles get up into those little fissures and they keep them open. And when those cracks stay open, it allows the natural gas to seep out. So you inject the fracking fluid in, and then you break the rock apart, and then you extract the water and the natural gas back out. And then when it comes back out, you have to separate the oil or the natural gas from the fracking fluid, which creates all kinds of wastewater that has to be treated. And like I said before, this is actually the cause of earthquakes. They're doing so much fracking in Oklahoma and in parts of Texas that there are earthquakes that are sizable enough that it's causing damage to structures. And so fracking, well, and there was a home up in Firestone, Colorado, which is just north of Thornton. And in Firestone, fracking caused natural gas to migrate through cracks in the ground, and it wound up seeping into the basements of homes. And a father was replacing the hot water heater in his basement. And when he put the new hot water heater in and lit the pilot, his home exploded. and threw his wife and baby daughter out a window. They survived, but the husband died as a result of underground migration of natural gas. It's deadly stuff, and we're doing it, right? So the full cost. All right. So let's get to coal. I know I'm rocking and rolling, guys, and I apologize um, for a just a full-on lecture day, but had to happen. So um, coal is the most coal is the most plentiful of the fossil fuels. The U.S. at current rate of use has somewhere north of 300 years worth of coal. Um, we're not going to run out of coal. Now, fortunately, we've stopped using it at the rates that we had been, so it's probably going to last us a little bit longer. Now, the reason that I was talking about irrational decisions before, and one of the irrational decisions that we make here in the United States is making ethanol and blending the ethanol with our gasoline. We started doing that, and right now it's at 10%. There's talk about increasing the ethanol to 12%. The reason we do that is because we want to take a resource that we have in abundance, which is coal, and we want to turn it into a resource that we are lacking, which is petroleum. And so what happens is we take another resource that we have abundance of, which is corn, and we, in the US, we make ethanol mostly from corn. And ethanol is just an alcohol that we can derive from corn. But it requires an energy input, and that energy input is coal. So you take coal and you use the coal, you burn the coal in order to make the ethanol, and then you blend the ethanol in to the gasoline, and you're decreasing our dependence on oil and using ethanol to do it. The problem with ethanol is it has a very low, often negative net energy, because so much energy is required to get the coal out of the ground, to use the coal to make the ethanol, and then what you get in terms of the chemical potential energy in ethanol is oftentimes either zero or negative, as a result of the energy inputs required to make that happen. So coal is the solid fossil fuel. Globally, it's right around 40% of the world's electricity. And again, that number's falling. It's falling in other countries as a result of the climate accord. And it's losing favor for a bunch of reasons. It's incredibly dirty. The biggest deposits of coal are in the US, Russia, and China. And obviously, these are the countries that use it the most. Again, this goes back to the Gapminder question that I asked you. If a country has huge deposits of a resource, are they more likely to use that resource regardless of the negative consequences associated? And the answer is yes. This is a great example of a profit priority taking precedent over a people or planet priority. And because it's abundant, it's cheap. And because it's cheap, it's historically been used the most. So what happens? We've talked about the generic equation of burning hydrocarbons. When we talk about this for coal, we're going to add a couple things. We're going to add sulfur oxides because there's sulfur in coal. And so when you burn coal, you release sulfur dioxide, which causes acid rain. It also releases a bunch of particulate matter. And obviously carbon dioxide comes from it. Now, because coal is found in different types of deposits than oil and gas, you're also going to get other metals like mercury, and you're going to get some radioactive isotopes as well. And when you burn those, you're putting them into the atmosphere for all of us to breathe in. So coal is the dirtiest of the fossil fuels as a result of that. So transitioning away from fossil fuels into nuclear. How are we doing on time? All right, we may get this in. All right, so nuclear power. What we're talking about here with nuclear power is primarily uranium. All right, and U-238 is the most common form of uranium that's used in nuclear power plants. Nuclear power is often cited as a savior by some people in the environmental movement because it does not release carbon dioxide during during the generation of electricity, and so that gives it a lower environmental impact. Nuclear power plants are incredibly safe. If I asked you to name three nuclear power plants, you would probably tell me 3 Mile Island. So make sure you get these down in your notes. 3 Mile Island, Chernobyl, and Fukushima. And the reason that you can name those three nuclear power plants is because they're the only three nuclear power plants that have had an accident in the last 60 years that we've been using nuclear power to make electricity. So they are incredibly safe. But when something does go wrong, it goes very, very wrong. And we'll talk about that. A couple of the other negatives associated with this is that you can use spent fuel rods. So that's what they call the uranium when it's no longer potent enough to generate electricity, and it no longer generates enough heat. They call them spent fuel rods, and the spent fuel rods can be used to make what they call a dirty bomb. And so there are former Soviet republics, like they call them the countries, they call them the stands, right? Kazakhstan and Uzbekistan. So those countries had nuclear power plants. They had uranium mines during the Soviet era, and they have governments that are not as stable, and there's great fear that we could have a proliferation of nuclear weapons as a result of unsecured spent fuel rods. The other piece is the radioactive wastes are incredibly long-lived. We're talking about 10,000 years as a starting point for this. And we do not, in the United States, we don't have a repository to store that waste. That radioactive waste that we generate at our nuclear power plants is stored at the power plants. And so they just keep these stockpiles. Basically, they keep them in steel casks submerged in water to keep the temperature from increasing and to keep it from becoming airborne. So there is no long-term storage method for this. And so there's pros and cons to nuclear. One of the biggest pros, obviously, is the lack of CO2 generated. So when we talk about the fuel cycle for this, it's similar to what we talked about with coal. You have to extract it out of the ground. You have to refine it in order to make the fuel. And they use that once it's been processed, they call it yellow cake. Because it looks like a yellow flour once they've extracted the uranium, the ore from the rock, and they've ground it up. It looks like cake, and then they put it into cylinders, and those cylinders are called fuel rods, and then the fuel rods go into the reactor, and in the nuclear reactor, the uranium goes through radioactive decay, and as it decays, it's releasing particles. And in chemistry, you learned about alpha and beta and gamma decay. And so as that decays, there's heat that is released from that decay. And the heat is used to make water turn into steam, and the steam spins a reactor. And we're going to talk more about that next class. And then they have to store the radioactive waste. And again, the storage of the waste is 10,000 years at a starting point for that. So there's the 10,000 year, the starting point for it. Some depending on the isotopes and depending on the reactor types, some of this stuff can be radioactive for all over 200,000 years. Again, we don't have a national repository for this. It needs to be buried. It needs to be buried in an area that is not active geologically. It needs to be buried in an area where there's no groundwater. And I'm out of time. And so what I'll do, guys, is I will, so I'm going to pause. All right, so to finish this up, in the US, as I said, there are no permanent repositories for it. The US government had put a plan in place to bury the waste in a place in Nevada called Yucca Mountain. And I'm sure you'll be shocked to learn that Yucca Mountain is a sacred site for indigenous people. And so once again, we've found a way to take something that is sacred to the indigenous people and really muck it up good. It's been canceled, and part of the reason it's been canceled is because of indigenous protests, and that's all to the good. But there's other factors. It was canceled because of cost overruns. It just became more and more expensive to even begin building a repository. There's concern that this particular location, Yucca Mountain, even though it's currently in an area that is not geologically active, meaning no earthquake activity, it's close to California, and there's concern that geologic activity can increase there. And then there's the kind of the geology of the rock. If there are any spills, there's concern that the spill could migrate into groundwater. The other part of the problem is, we have nuclear power plants spread out all over the United States, and these power plants would have to send their radioactive waste, across the country so that it could be stored. So imagine having, trains loaded with uranium or tractor trailers carrying uranium, and there was an accident. It turned into a massive national security issue, and that kind of put the end to it. So right now the plan is that there is no plan, and so as a result of that, we haven't built a new nuclear reactor in the United States since the late 1970s. As a result of 3 Mile Island disaster, but also because it's incredibly expensive to generate electricity using nuclear power, and we have these issues associated with disposing of the waste. So the last thing, I said that nuclear power is incredibly safe, and that the only nuclear power plants you know about are the ones that have had a disaster. And the disasters range from, 3 Mile Island, which is in Pennsylvania outside of Harrisburg, relatively small. It was a release of some radioactive steam. I don't think anybody even got sick as a result of that. And then you go to Chernobyl, and I can't remember what network, an HBO or one of those did a series on Chernobyl, and it was pretty faithful to what happened. And so if you get the chance, that's worth checking out. Chernobyl was an unmitigated disaster, spread radioactive waste across the world. It spread all through what was the Soviet Union, and even landed in the United States. That's how far the waste spread. The most recent one was Fukushima, and the Fukushima disaster happened in Japan in 2011. There was an earthquake off the coast. The earthquake damaged the power plant, cracked the floor, cracked the core. So the core is always submerged in water, and so when the core cracked, the water drained out. So radioactive water leaked into the ocean, and the only way that they could prevent the core from melting down and exploding was by pumping seawater into the core in order to keep the temperature down. But again, the more water you pump into the core, the more water is leaking through the cracks in that containment vessel, and so they're still, like right now today, they're still pumping seawater into the reactor to keep it cool, and so we still have radioactive waste seeping into the Pacific Ocean, which, if you're a sushi lover, that's a problem. We're already starting to seeing isotopes in certain fish that are caught off of the coast of Japan. Now that disaster happened because of, it was a natural disaster, but it could have been prevented had a little more planning taken place. The company, the nuclear power plant company, was cozy with the government. The government did not require them to build in all of the protections that were recommended, and so that's things like the seawall being too low, because the tsunami came and damaged it. They put backup generators on the second floor of, or on the first floor of a building instead of the second floor. And when the tsunami hit, it destroyed the generators. And so just everything that could go wrong in this case did. And that's the biggest issue that people have with nuclear power, is that when something does go wrong, it goes very wrong. And unlike 3 Mile Island, a lot of people have died as a result of the Fukushima disaster. All right, guys, that was a sprint. And thank you for tuning in, but getting this one done on time gives us the ability to really get through the content we need to prior to the end of the semester. So take care. Happy Friday or Monday or whatever day it is that you're watching this. I miss you. I'll talk to you soon.